So we'll just do this one in a group, so I don't want to dive into separate rooms yet. But so we sort of left off talking about pages. We sort of went back and covered what paging is and how page tables work and how the TLB works. So I wanted to know, sort of chat with you about we talked about sharing, the fact that processes, because the frames are the same physical place in memory, processes can share code, share data by sharing these pages. So I wanted to ask, like, what would some possible security implications be of processes sharing code or sharing data? So what do we think?
Maybe like if it could try to overwrite code or something.
Yeah, so like if processes are sharing like a shared library, what happens if someone attacks a not so secure process and overwrites the shared code with some, exploit code? So basically, we have to be very careful once we start sharing things between processes, because we don't necessarily know that like the process that I'm sharing this library with is secured properly. Maybe my program is perfectly fine. It doesn't have any security vulnerabilities, but this other process has a security vulnerability, and then sharing can allow a non-secure process to affect the security of a secure process, essentially, because of the fact that we're sharing it. So that's wrap up from last week. So again, just sort of making sure we understand that each of these page tables does have valid bits. They probably have these extra permissions that are execute, read, write. They might have sharing between different pages. So we do store additional information in this page table structure. So it's not just the page number, the frame number. It's probably a few additional bits as well. So we might expect that one of these entries is at least the same size, or like maybe double the size of whatever address sizes are. So if we have 48-bit addresses, we need 36 bits for each page number, frame number. That puts us up to 72 bits. We're probably just going to extend it to 128 bits to match up with the structure of caches and things like that on the system, which means we have these extra bits to indicate things like permissions, sharing, whether it's backed by a file, all this sort of stuff. And we compress that into 128 bits that gets stored as the actual entry in the page table. So we can kind of assume that that's probably about how big these are in the system, possibly bigger as well if we want to store even more information in there. And this is all tracked as part of the page table. So now let's move on and talk about the fact that so the page table itself is fairly large, right? We have in a 64-bit system, we have 2 to the 64 unique addresses because we can use each bit, give it either a value of 0 or 1. We have 64 bits, and so we have 2 to the 64 possible addresses that we can store in this page table. And that means that we cut out the number that go into the offset, but still we can have a very large number of entries in a page table. So a single level page table, if we have a 48-bit address space and we have maybe 128-bit, or even if we say the minimal amount of bits, like 36 or so bits for the 4 kilobyte pages, the number of bits we have left with 4 KB pages, 4 KB is 12 bits used. So we'd end up with like 2 times the 36 bits, which is about 2 to the 50 bytes, which is a petabyte of space. So for a full single page, single level page table, we would require a petabyte of space for a 2 to the 48 address space, which is not reasonable, right? That's just way too much space to be using for the page table structure. So we can't assume that a system can do this. It was a little more manageable in a 32-bit address space, because then we had 2 to the 20th times the number of bits. So, you know, a megabyte times however many bits we were using, which is not that bad. It's still a lot of space in the 32-bit address space, but it's not an unreasonable amount. Whereas like a petabyte of space is an unreasonable amount. Like we can't expect to actually use that much space to store this. So sort of keeping in mind that we have all of this address space, we can't actually feasibly map it to a page table if we're using all of it. So despite the fact that we have all of this address space available, we don't always end up actually using all of that address space. We usually use bits and pieces of it. So there are a few ways that we can solve this problem. So the first way is to use a 2-level page table, and this is what some of the homework was, or some of the reading quiz was based on. So in a 2-level page table, we divide the bits used for the page number into 2 separate page numbers. So we have an initial page number, which is some number of bits, and a second page number, which is another set of bits. And then we have the same page offset that we've had previously. And so what this allows is that we can basically have all of the mappings for the first page number. So we have a smaller page table that has pointers to the second level page tables. We use the first 10 bits maybe to index into the first page table. So that we pull out those bits, we use that as an index into an array. That finds us a pointer to the next page table. We then use the second set of bits, so P2, as an index into the second level page table, and that finds us our actual like page to frame mapping and all of the extra, you know, valid bits, protection bits, etc., that we would actually store. So I have a little diagram here. So this is roughly what we're talking about here in our setup that we've had before. So now we split this address into you know, a table that is now 1 bit. Let me insert another table here. So we can have basically this setup where we have P1, P2, and page offset. For our 4-bit addresses, we're going to have 1 bit for P1, 1 bit for P2, and 2 bits for the page offset. So that's how we're dividing our addresses up now. So if we look at this setup, then we have, you know, every address is going to start with a 0 or a 1. That's our index into the first level page table. So, you know, address, let's use as an example, address OX D. So OXD is going to turn into, what is D? 1101. So that means that our P1 is going to equal 1. P2 is going to equal 1. And then page offset is going to equal 0, 1. So we're just pulling out the first bit is P1, the second bit is P2, the last 2 bits are the page offset from the structure. So we can look this up in the page table just like we would have before. We say P1 is 1, so we're going to follow this link here to the second level page table. So we basically, the first page table just has pointers to the next page table. And that's all it does, is just points to the next level that we need to find. We then go to the second level page table, and we find that the page number there is 1. So we're using P2 here to index into that. We know then that page 1, 1 maps to frame number 1, 1 and is valid. So we can map from this address D into the frame that holds that address in physical memory. So the big benefit of this is that we can not have parts of this map. So let's say that we don't actually, you know, we have a page 00 is also grayed out. Or which one do we want to do that for? Maybe not that one. So page, undo that. Let's say page 1, 1 is also grayed out. So we don't actually have a mapping for either of these bottom page tables. We could very easily just not have this second level table here. And now we just have a pointer to the first one, which is all of the things that start with 0. We don't actually have to allocate a page table, a second level page table for the mappings for 1, 1, and 1, 0 until we actually have some accesses that access those pages. So until we allocate memory in that range, we don't have to have a second level page table allocated for it. So this allows us to sparsely map page tables for the memory that we're not using. So that way, if we have this very large 2 to the 48 or 2 to the 64-bit address space, we don't actually have to have a page table that covers all of that. We just have to have it covering the parts that we're actually using in physical memory. Okay? Sorry if you can hear that, by the way. My dog is upset about something outside. Probably the cat that lives outside next door. This public enemy #1 for my dog. So, okay. So this is the main benefit here, is that we don't have to map all of memory. We can just map the parts that we're actually using whenever we have this in a 2-level page table. So we can avoid mapping all of this space, and we only have to use the parts that we are currently accessing in memory. Okay. Any questions on that so far? Okay. So this does require now that this first level page table, each of these entries is going to be, we're indexing based on the page number, and then we're finding a, 32-bit or a 64-bit pointer. Sorry, excuse me for a minute. I'm going to go put her in a different room. We're back. Okay, sorry about that. She went straight to her crate because she knows she's bad, or knows she's being bad. Okay, so sorry, that was distracting me a little bit there. So we can extend this approach as well. So we don't have to have 2 levels. We can have 3 levels. We can have 4 levels. We can have as many levels as we need of this page table in order to fit this appropriately. So, in a more realistic system, we might have 64-bit addresses. We have 12 bits for the page offset. If we have 64-bit addresses, that still leaves 52 bits to split up between these two, which probably means 26 bits here, 26 bits there. That's still a lot of space for 26 bits. 2 to the 26 times what we end up with here is going to be 2 to the 26 times the number of bits for each level, which in the next level pointer in a 64-bit system, that's going to be times 64 bits, which is still quite a bit of space, right? This is 2 to the 26 times 8 bytes. So we're still taking up quite a bit of room if we have the setup that we have, these 26-bit pointers. And then the second level is going to be, 2 to the 26 times whatever the size of page table entry is, which is, 2 times the size of the page number and frame number plus any additional bits. So this is still a good bit of space. So we can, trim this down a little bit more if we want to, and have a few more page numbers that we can use. So we could also have up to maybe 4 levels where we have P2, P3, P4. Now we can trim these each down to 13 bits, maybe something like that. 13 bits. per entry. Now our first level table is just 2 to the 13th times 64 bits. Then we have a second level that is 2 to the 13th times 64 bits. A third level that's 2 to the 16th times, or 2 to the 13th times 64 bits. And then a final level that's 2 to the 13th times the size of the page table entry. So now that's getting to the point that it's fairly reasonable, right? This is, maybe, a couple kilobytes of space per page table that we have to have in this system. It's no longer unreasonable to make each of these tables individually. Now, this does add some overhead since, of course, we have all of these additional pointers. If we did map this entire 2-level page table, this would be more space than the petabyte that we had for a single level page table. However, because of the fact that we don't usually use all of this memory space, we can design it this way and save a bunch of space in reality because of the fact that we're sparsely using memory. Okay. So I may ask you questions about this on the exam, to say what are the, what bits would be representing the, second level page table, or have you do a lookup based on some deeper nested page table and figure out what the frame number is or something like that. And, basically do these sort of computations, how big is this depending on, what is there. So it's important to remember, like, the first couple levels until we get to the last level of the page table with a 2 or 3 or 4 level page table, everything is going to be an address sized entry because we just have a pointer to the next page table. The final one is where we have to compute like how big the page and frame numbers are and how many bits we're using for the actual page table entry. Okay. Any questions on this? Oh, please bring Woofer into view. She's a little far over right now. She's actually hiding behind a pillar. I will, if she comes over to somewhere I can point the camera at her, I'll let you see. I'll let you see Misty. So, sorry. Any questions on non-dog related things? Okay. So let's move on then to the other options that we have here. So there are a couple other approaches we can use to make this feasible. So the other approach that we have is that we can use a hashed page table. So we talked a little tiny bit about hash tables in the beginning of class. This is just using a hash function to map from the address to the page table entry. So rather than taking the bits or taking a hash of the page number to map into some table. So rather than taking the bits and sort of doing this lookup, we can have a hash function that restricts it to a smaller number of entries. So the setup here is the same as before. We have the same 16 bytes of memory. We have the same 4-byte pages, but now we're using a hash table instead. So we're just taking actually like the modulus. So here our hash function would be, our hash function here would be hash of VPN equals VPN mod 2. So it's basically just, is this even or odd, right? For the page number. And so we can have the same setup, right? Where we take the hash of the page number based on what we're looking up. And then instead of having the sort of pointer to the next level page table, we have a pointer to a linked list of all of the pages that we have mappings for that collide with that hash number. So right here, we don't have enough unique entries to have every page number mapped to a different entry in this page table. So we have, 0, 0, and 1, 0 are both going to map to hash 0. They are both mod 2 going to be 0. So they're both going to go to that entry. So if we had an entry for 1, 0, we would have to have a linked list that chains to the next page table entry here. Since we do have entries for 0, 1, and 1, 1, we can see that when we go to hash page number 1, so when we do 0, 1, or 1, mod 2, that's going to be 1. If we do 3 mod 2, that's also going to be 1. So this is the remainder operation, right? So they're both going to map to hash of 1, which means we go to this list, and that list starts off with 0, 1, which has the mapping 0, 1 to 0, 0, and then it's valid. And then we have the next pointer, which points to the next thing in that linked list. So because we have two things that can collide in the hash table, we have to have this linked list that points to the next entry, and that also has 1, 1 maps to 1, 1 and is valid. And then when we get to the end of the list, we just have a null pointer to say that there's no other entry. There are no other entries here. So this is a reasonable way to restrict the page table to a smaller number of possible entries. So, you know, for example, we can say I want my page table to be sized at 1 megabyte at maximum. And I can choose a hash table or a hash function, basically say I'm going to give only the number of entries that will size it at 1 megabyte, and design my hash function to make sure that everything goes into that 1 megabyte of space. So this is kind of a nice way to do it, that it doesn't actually matter what the size of the address space is, so that 2 to the 64 or 2 to the 32 or 2 to the 48 no longer matters. All that matters is how big I want my page table to be, and I design my hash function around that. Obviously, the less entries we have in this hash table, the more likely we are to have collisions and have to look through a much longer linked list of entries in order to find the one that actually matches. So once we go to the correct hash number, then we're stuck with an O of N search to go through all of the possible entries and figure out what's in there. Okay. Any questions on hash table or hash page tables? Okay, great. So then finally, the last one that we should talk about is the inverted page table. So again, this is a way to handle the sort of space blow up of a large page table. And what this does is, instead of having a per process page table, we have a page table that is associated with each frame. So we essentially have this, where we have two processes. They each map some pages. And I'm actually going to gray this one out. I shouldn't have copied it this way. Because we can do this. We'll talk about it in a minute. So we have these different pages mapped into physical memory. And here, instead of keeping a page table per process, we're just going to keep that information with the frames themselves. So now we have essentially a frame table that has frame to page mappings and keeps track of the pages and process IDs that are associated with each physical frame. So the benefit of this is that it is appropriately sized, right? We have all of this hardware that's already set up to handle the fact that we have pages to frame mappings. We just add in some additional hardware along with that to keep a page number and a PID along with each frame. The problem with this is that it is either very sort of energy expensive or you know, performance expensive, because now to find out if I have page number or I have virtual address 0x7, I have to search through every frame in order to figure out, is this the frame that is mapped to that page? So it's not too bad for page, you know, 01 stuff, because that's the first frame we're going to look at. We're going to find that page number and process ID pair. If it's the last one, though, we've had to look through every single frame in order to find that. Or we have to use something like a content associative memory. This is, you know, very expensive hardware that basically does all of these comparisons at the same time, which can be, you know, thousands of comparisons. That's a lot of hardware that's all firing at the same time, using up a lot of energy in order to do this. So that is an option we can make. We can make it either, you know, performance intensive, where we have to look at all of these entries and then figure out which one it is and then send the data back, or we can make it very energy hungry and do all the comparisons at once against the page number PID pairs, and then output the correct result from that. But either way, it's going to be expensive in some way to do this. So this can be a nice solution. However, it just, you know, it is very expensive as a solution. whereas the other solutions are not quite as bad that way. So question for you to talk about briefly is, can processes share memory in a system that uses an inverted page table? Why or why not? So go ahead and disperse into Discord groups and go ahead and chat about that for a minute or two. Okay, what do we got? Okay, so let's I think you can stay in the same Discord rooms because I'm putting voice over Hangouts. So if you want to just stick in those rooms, I think that's fine for the next next time a question comes up. So yeah, I think we've got it eventually here that essentially the problem is that we have this one PID and one page per frame. So we actually can't share memory in a system like this because of the fact that we don't have this. We could maybe have, like we have with the TLB, we could change this to an ASID where it's an address space identifier. But then we need some sort of mapping from processes to which address space identifiers they have. And we need to know like what pages are associated with those address space identifiers. So it's a lot more framework, a lot more setup to try to get that to work. And it's probably like a very complicated, convoluted hardware structure, which means bugs, you know, which means for companies that make hardware things like, you know, call or, you know, taking back things and paying for them, recalls, that's the word I was looking for. So it's not very feasible to do this in hardware. So we only can really have this set up that we have the page and PID pairs, which means no shared pages in memory, which then means like we have to have multiple copies of libraries in memory at the same time in physical memory, one for each process that's using that library. We can't share data between processes. So in certain setups where, you know, we don't want sharing or we don't care about sharing, this might be reasonable. But for the most part, it's not going to be that reasonable. So let me just update this. No, because there's only one PID page number per frame, and adding more would be too complicated. So this was a thing on older systems, so like Spark and PowerPC systems used inverted page tables to minimize this. So Spark probably never used. PowerPC, if you used an older Mac before Macs went to Intel chips, this was like 2010 or so, I want to say that this happened. Right around then that Mac computers started using Intel chips instead of PowerPC. Before then, you would have maybe had a system with an inverted page table, but nowadays it's mostly going to be standard page tables in software. And I think generally what you're going to see in real systems is this two-level page table. And I do want to say that this is sort of a nice like common use data structure if you have things like addresses that you need to split up and that are sparse. So you can use these as like, you know, anytime you have things that you're going to organize into a data structure based on the address or based on a large number that you can sort of chunk up into smaller portions, this can be a nice way to store that while maintaining some amount of like saved storage space based on the ones that you're not using currently. So I sort of recommend, you know, learn this data structure, get a good feel for it, because it is sort of more generally useful in practice as a programmer. I've used these a couple times, though that's mostly with things that are related to address space, like pointers anyways. So any questions on these three different ways to set up a page table and sort of minimize the amount of space that we're using, make the space feasible for a 64-bit address space? Otherwise, we will move on. Okay. So let's get to the last topic for today. And the last topic on paging, we're going to have the reading quiz for Wednesday should be out. Sorry on the sort of short fuse on that one. It shouldn't be too difficult to find the answers to. I tried to make them pretty easy for this one. So we'll have a reading quiz on Wednesday and then another one on Friday that we're going to talk about the way that we decide which pages to swap in and out of frames when we have memory that's full. These are sort of, you know, useful algorithms to know. So we'll talk about that, but the rest of that's going to be the end of paging for us. And then we're going to move on to some other OS topics. So the last thing we have to really talk about is swapping. And even here, we don't need to talk too much about it. Just make sure you know how this works. So we have the setup where we have frames in memory, and we have pages that are in the virtual address spaces. This works really well if we have the setup that we have two processes and they are mapping only the number of frames that we have here. However, we might have a problem if process 2 also wants to map one more page into memory, right? If they want to map a green page in somewhere, now we don't have a frame for them, and we need to decide what to do about the fact that we have more virtual memory than, or we have requested for more virtual memory than we have physical memory. So without paging, our solution is usually to just say, or without sort of paging that allows some pages to be in memory, some pages to be out of memory, our solution is usually to just say, okay, well, either stop that process, make it wait for memory to be available, or to schedule a different process. But basically, we're going to deschedule something so that the other processes can use that memory. So this is standard swapping. Is essentially the same thing, where we have too much memory in use in physical memory, and we take a process out of physical memory and move that process's memory to secondary storage. So this would be like a hard drive. So this is where you basically like on Linux, if you've ever installed Ubuntu or any other Linux system, it will create the regular system, like where all of your stuff is stored, like all of your files, and then it'll create a swap space as well. And the swap space is where it puts things that don't fit into physical memory. So it's another place on your hard drive that we copy process memory into whenever we swap processes out. So what does that make expensive, or what does that make more expensive?
Context switches?
Yeah. Yes, I know it's in the notes, but yeah, context switches are sort of the big thing here, right? That when we have a context switch now, if we have swapping, we are copying large blocks of memory out of physical memory and onto a disk. And we know that secondary storage is usually slower but larger than main memory. So a hard drive will be slower to access, which means we're using something that's slower than the main memory speed, which means we're limited by the secondary storage speed. And we have to not only swap out the one that we're getting rid of, but we have to swap in a new process sometimes, which means that overhead happens twice essentially. However, this does allow us to use more virtual memory than we have physical memory. So we can, have that illusion for the programmer that they get the entire memory space, that they can use all 2 to the 64th bits. And if they use all of those bits, it's going to be fine. They're all of those bytes, it's going to be fine, that we can, manage that memory for them. So we can, do a couple things. We can swap out idle processes. We can try to find, things that aren't currently using the memory. But we do, with standard swapping, we swap out the entire process. The sort of better way to do this is to only copy some of the pages out. So, with the setup we have here, let me duplicate this and then get rid of some of the stuff. So if we delete these, we have physical memory now. We have the frames mapped in. Here we can either have, frame 10 is unmapped, and frames 1, 0, 1, and 11 are all mapped. So this is when process 1 is running, and then we could have, maybe process 2 uses this one, and these 2 are unmapped. So we could have either of those 2 setups if we use standard swapping. And that means that, we can only run one of these processes at a time. Each time we swap them out, we put the other ones on disk. The memory that we're not currently using goes on disk, and everything else comes back in. With sort of newer form swapping, we can do something like this instead, where we have some of the memory mapped to process 1, some of the memory mapped to process 2. In the event that, process 2 is not really using frame 0's memory that often, and process 1 is really using that memory constantly, we might just be able to swap these back and forth so that when process 1 is using page 1, we replace page 0 from process 2 with page 1 from process 1. Whenever process 2 needs to use that page, then we swap it back. So here we can sort of bounce back and forth between individual pages that are in use by these processes and sort of put them on disk and swap them out from disk as necessary, rather than swapping everything at once and not letting a process run at all. So here we have to have some overhead each time a process accesses memory that's been replaced, but we save the massive context switch overhead, because now when we context switch, process 2 gets to run, its memory is mostly there. Process 1 gets to run, its memory is mostly there again. The only thing that's missing is that page 01 that we might have to load if we swap back in. So this is sort of a lazy or on-demand paging instead, that we only pull things in that we need for that particular process at this particular time. So that's when we generally talk about swapping, that's what we're talking about, is that it's one page at a time, not the entire process. Now, on the other hand, the benefit to standard swapping is that once we have the pages in memory, we're never going to get to a point that we access memory that's not there, because we've already swapped everything in. Whereas with standard paging, we might run process 2 then, and we have to swap in page 0. So we can sort of hit in-flight issues as we're running a process with on-demand paging, whereas with standard swapping, we wouldn't have that issue. So there are some sort of cases where standard swapping can be better. For example, like critical embedded system types of applications where timing is really critical. We don't want to have a swap in have to happen while we're running, or we don't want some other context switch to cause a swap out to happen. So there we might want to make sure that when our process starts to run, all of our memory accesses are going to be roughly the same speed. They're never going to have to go to the disk speed of pulling memory from disk back into memory. Back into main memory. So there are some advantages to standard swapping, but most of the time we're going to be just using on-demand swapping here. So then the final thing to talk about today, and then we'll be done, is the use of flash memory. So mobile systems can't really use swapping. This is because flash memory can only be written to a certain number of times. Like all of your flash drives, anything that you have like that, has this issue that the hardware behind it, the electronics that run flash memory, have sort of wear out properties, where if you write to them too many times, they will be no longer usable. So in a flash memory system like a phone, where most of the storage, if not all of the storage, is going to be flash, we can't use something like swapping, because we're constantly running processes. We might constantly be swapping into and out of that memory. And if we're constantly doing that, we're going to hit the wear out factor of that device way faster than we should. And the device is going to go bad. So it'll be written a number of times and before it's no longer usable. And so we can't use that to free up physical memory. So things like iOS instead will actually just ask a process to relinquish unused memory when the physical memory is oversubscribed. So it'll say, it'll sort of go through the processes and say like, hey, can you give up some memory? Are we able to collect some memory here? Is RAM the same? Does it have cap for rewrite? So standard DRAM does not have a cap for that. It's just capacitors that get charged up and they get refreshed every once in a while. Once in a while being like every 64 milliseconds. So it does not have a cap. We can charge capacitors as many times as we want. But the DRAM stuff does have this cap for rewrites. Or not DRAM, flash memory does have this cap for rewrites. So you can talk to if you have more questions on RAM, you can ask either Midshipman Beck, Ross, or Ralston. They know a little bit more about this. So we've been looking into a project actually looking at novel memories, and a lot of these are flash based. So the main one that's available right now is Intel Optane, is a flash based memory, and then some things like Memristor's MRAM that are newer memories but do end up having those same caps, although these are usually a lot longer lived than the flash memories that we have now. So if you have follow-up questions, ask them about their research. But yeah, so we have this cap that we can't write as much, so we don't use swapping. We just ask for processes to basically garbage collect themselves, you know, find free memory in their space, compact as much as they can, and then free up some of that physical memory. Okay. Any questions on anything that I've covered today? Otherwise, I didn't have time to make a Kahoot, so I couldn't get that for today. So we will probably have one. I know we've missed 2 in a row, so I'll try to get one for Wednesday. Any questions? I think the dogs moved to the couch, so yeah. The big woofer, I think, there.
So cute.
Yeah, and then the little one that's crushed in under her. Unfortunately, the poor guy. So yeah, those are Brock and Misty, our dogs. So.
Pokemon characters, I like it.
Yeah, and so I will share the PowerPoint with you. Let me do that now so I don't forget. So, okay, that should be in Discord now. So great. If there are no other questions, then I will see you on Wednesday. Don't forget about the reading quiz, and let me know. By the way, I am available. I wanted to just mention, based on Actine Waters' email this morning, that I am available for EI. Same as usual. It's on my calendar. You're welcome to sign up for. You're welcome to sign up for appointment slots whenever you want to. Just go to my calendar, and I think that's still tinyurl.com/Delosier. It should be in Piazza as well, but you can click there, sign up for an EI slot. It'll just be obviously via Discord or Hangouts or something instead, so that we can meet virtually. But I am still available, so if you have questions on homework, on projects, anything like that, feel free to contact me. I'm happy to chat with you more, or lecture topics. I'm happy to talk about this stuff. So have a good rest of your day, and I will see you on Wednesday.
Have a good day, sir.
Thanks.
Thank you, Professor.
Thank you.
Yep, see you.
Yep.